We continue with the special functions playlist by looking at gamma function as promised. Gamma function. It's one of the special functions we consider. We already saw it under the introduction in the previous video. So let's go ahead and take some deep look at gamma function. So first of all, the topics covered here will include things like factorial extension, Euler integral, functional equation, reflection formula, duplication formula, poles and residues. We saw poles and residues under differential under complex numbers, right? So we saw poles and residues. So we're going to see poles and residues here too. Then Stirling approximation, digamma function, polygamma polynomials, worked examples, and some Python implementation. So let's go straight to it. We already saw in the introductory video that a gamma function is one of the most important special functions in mathematics. It generalizes the factorial function to non-integer and complex variables. So, factorial functions, we know factorial functions to be something like if you have 5 factorial, that's 5 times 4 times 2 times 2 times 1. But gamma function helps us to generalize that even for non-integers, maybe fractions or even negative numbers and complex values too. So the gamma function appears in calculus, complex analysis, probability theory, quantum mechanics, differential equations, and statistical mechanics. The gamma function is defined by gamma of z equals integral from 0 to infinity t raised power z minus 1 e raised power minus t dt for the real part of z greater than 0. Okay. Now, in the last video, one of the worked examples I did that I solved by hand was showing that gamma of z plus 1 is equal to that showing that gamma of z plus 1 is equal to z gamma z, yeah. So that was the kind of thing we saw there. Okay, so the motivation for gamma function is the extension of factorials. So recall the factorial function n factorial, which is 1 times 2 times 3 up to n. So if you have 7 factorial, that means 1 times 2 times 3 times 4 times 5 times 6 times 7, like that. Then examples, you have 1 factorial that is simply 1, 2 factorial that is 1 times 2, which is 2, 3 factorial that is 1 times 2 times 3, which is 6, 4 factorial that's 4 times 3 times 2 times 1, or 1 times 2 times 3 times 2, if you like. That's 24 now. Now the question it becomes this: can factorials be extended to non-integers such as half factorial? Can we find half factorial? That's the question. So the gamma function provides this extension when you now deal with things like half factorial. Of course, we also know that 0 factorial is 1. So gamma function is a very cozy place to prove that 0 factorial is 1, right? So the gamma function is defined by Euler's integral. So here we're looking at Euler integral definition. The gamma function is defined by the Euler's integral, that gamma of z equals integral from 0 to infinity t raised by z minus 1 e raised by minus t dt. Now we could as well say gamma of z plus 1 is integral of 0 to from 0 to infinity of t raised by z e raised by minus t dt. So if you have z plus 1, we have t raised by z. If you have just z, we have t raised by z minus 1. We can even have gamma z minus 1. That will now be t raised by z minus 2 e raised by minus t dt. So whatever happens, just pay attention to what you have here. So this integral converges for the real part of z greater than 0. So interpretation is that t raised by z minus 1 provides algebraic growth, while e raised by minus t provides exponential decay. So it's more like you have an interaction between growth and decay happening at the same time. Together, they create a convergent improper integral, right? So you have one decaying, you have one growing, and then together they create a convergent improper integral. Then you have functional equation. So the gamma function satisfies the recurrence relation gamma z plus 1 equals z gamma z. That was what I did in the last video. One of the examples I did was to show that gamma n plus 1 is equal to n gamma n, or if you have gamma z plus 1, that's z gamma z. Or even if you like, gamma z is equal to z minus 1 gamma z minus 1. Anyhow, you have it. So this is the continuous analog of the fact that n plus 1 factorial is the same thing as n plus 1 times n factorial, right there. Okay, so the functional equation is the key property that connects gamma with factorial. So this gamma equation is the key thing that connects gamma with factorials. So proof of functional equation now. So the proof that was what I did in the other video, right? So I'll just run through it slowly. So if you start with gamma z plus 1 to be integral from 0 to infinity of t raised power z e raised power minus t dt. Then if you use integration by parts, so you can so integration by parts is about you pick a part, you pick a part which is easy to differentiate, another part which is easy to integrate, and then you differentiate, integrate, and put them together and get the result. So t raised power z is easy to differentiate in that if you differentiate z minus 1 times, you get a constant. If you integrate z times, you get 0 at the end of the day. But e raised power minus t, it keeps going. So it's better to pick this as what you're integrating. So if you let u be t raised power z and dv is e raised power minus t dt, then it means u is e raised power t z means du is z t raised power z minus 1 dt. While dv equals e raised power minus t dt means that v is minus e raised power minus t if you integrate this side now. So now you can put it together by applying integration by parts. So gamma z plus 1 is then integral from, so you need, generally speaking, right, that's integral of u dv, okay, integral of u dv equals uv minus integral of v du. So you just put all of that together and you have that. So you have this is now u, that's t raised power z, and v is minus e raised power minus t. So that's why this minus here is what you have, a tz e raised power minus t from 0 to infinity. If you put infinity, e raised power minus infinity goes to 0, so it makes everything go to 0. If you put 0, when t is 0, whatever this is, everything goes to 0 again. So this whole thing goes to 0, as you can see here. And then for this now, you have v du, right? So v here, you have minus e raised power minus t. But here was supposed to be minus, right? So the minus and minus becomes plus here. And then you have zt raised power z minus 1. So this z comes out here and you have t raised power z minus 1 because the variable we are looking at is t. So that's why z is more like a constant here. So by the time you're done with that, as this goes to 0, you then have z integral from 0 to infinity t z minus 1 e raised power minus 2. So if gamma z plus 1 is t raised power z e raised power minus t dt under the integral, then this thing, t raised power z minus 1 is simply gamma z. So that's easy proof that gamma z plus 1 is the same thing as z gamma z. So now, we then see that gamma extends factorials. Gamma extends factorials. So using gamma z plus 1 equals z gamma z, based on what we've established already, we can then see that gamma 1 is equal to 1 gamma 0, right? Yeah. That'll be one, gamma 1 is 0 gamma 0. No, okay. No. We're not saying gamma 1 is not 0 gamma 0, but the fact that gamma z plus 1 is z plus z and gamma 1 is 1. If you can prove the two that gamma 1 is actually 1, then we obtain gamma 2, which is 1 gamma 1, which is 1. Then gamma 3 is 2 gamma 2. So that's 2 times gamma 2 is 1, so you get 2. Then gamma 4 is 6, which is 3 gamma 3. So that's 3 times 2. Gamma 3 is 2. That's 6. Thus, we can say that gamma n plus 1 is simply n factorial. So you see gamma 4 is 3 factorial, gamma 3 is 2 factorial, gamma 2 is 1 factorial for positive integers established. So then can we then compute the gamma of 1 over 2? So one of the most important identities in mathematics is the fact that gamma 1 over 2 is square root of pi. So we derive this result carefully, step by step. Start with the gamma function definition that gamma of z is equal to integral from 0 to infinity t raised power z minus 1 raised power minus t dt. So if you now set z to be half, because you're looking for gamma of z, so it means that gamma half will be integral from 0 to infinity of t raised power z is half, so half minus 1 e raised power minus t dt. So if you simplify the exponent, half minus 1 is simply minus half. So we have that gamma half is integral from 0 to infinity t raised power minus half e raised power minus t dt here. Okay, so next, you now substitute, use the substitution. You can then say here now, let t, so for this t now, you say let t be x squared. So we are substituting, the variable is t, so we are substituting that with x squared. So that means if you differentiate t equals x squared, dt dx is 2x. That means dt is 2x dx. So also, then we have t raised power minus half. T raised power minus half means, since t is now x squared, so we have x squared raised power minus half. So 2 cancels half. So we get um 1 over, this should actually be 1 over x, I believe. Yeah, because x cancels x here. So this should be 1 over x, not 1 over x squared. Okay, well, I mean, that's more like, okay, well, doing the indices, that's 1 over square root of x squared. That's still fine, but I could have just cancelled it. So that's still 1 over x, but that's x. So it ends up being 1 over x either way. So if you take x to be greater than or equal to 0, right, square root of x squared is x, and 2 raised by minus half is 1 over x. So I was just going to do it this way. 2 cancels 2, so we have x raised by minus 1, which is 1 over x that we end up getting at the end of the day. So you can substitute into the integral. So gamma of 1 over 2 is equal to integral from 0 to infinity, 1 over x e raised to minus x squared, 2x dx. I mean, what we have done there is to say this t raised to minus half is simply 1 over x. And on the other hand, t now is x squared. So we have e raised to minus x squared. Now, the t is, okay, e raised to minus t dt. Yeah, no, dt alone is 2x dx. So we have this 2x dx right here. So we can then bring out the 2. All right. So we have 1 over x. X cancels x here. So we bring out 2. So we have 2 integral from 0 to infinity, e raised to minus x squared dx. Now this now becomes, this looks pretty simple, but then it becomes a very big issue. So gamma half now is 2 integral from 0 to infinity, e raised to minus x squared dx. So normally, if you just say maybe let u be x squared and we differentiate, but it doesn't work that way because it's not as straightforward as it is. So we now derive the Gaussian integral, that integral from, integral from minus infinity to infinity, e raised to minus x squared dx is square root of pi. That's where we are going to. So we want to show that this is equal to square root of pi. So now let I be integral from minus infinity to infinity of e raised to minus x squared dx for starters. So if you square both sides, so you have, if you square both sides, you have I squared. So I squared means you now have integral from minus infinity to infinity of e raised to minus x squared dx. Because you have squared it now, you can also now say that's integral from minus infinity to infinity of e raised to minus y squared dy. So they are functionally the same. So then if you combine the integrals, you have y squared equals integral from minus infinity to infinity, integral from minus infinity to infinity of e raised to minus. So add up, you have minus x squared plus y squared dx dy. So it now becomes so a kind of surface integral. So this is a double integral over the entire plane now. So that's the double integral there. So now we have to now do something. So we convert to polar coordinates. So first of all, if you say x is equal to r cos theta and y is r sin theta, so then it means that x squared plus y squared will be r squared cos squared theta plus r squared sin squared theta. So if you factorize r squared, that will be r squared into cos squared theta plus sin squared theta. That will be 1. So that means x squared plus y squared is r squared. So x squared plus y squared there will be r squared. Then the Jacobian then gives that dx dy is r dr d theta. If you do the Jacobian of this, we get r dr d theta. Thus, we can say then that I squared is integral from 0 to 2 pi. Now in polar coordinates, we have r and we have theta. So we have line and angle kind of. So for the line, we have 0 to 2 pi. For the line, we have 0 to infinity. For the angle, we have 0 to 2 pi. So it's now e raised to minus r squared, r dr d theta, because the whole of this dx dy now is r dr d theta as we have here. So if we separate the integrals, we have integral from 0 to 2 pi of d theta, that's the only angular part, and the linear part is integral from 0 to infinity re minus r squared dr, like this. So if you compute the angular integral, that's integrate d theta. Integral of d theta is theta. So that's theta from 0 to 2 pi. That's 2 pi minus 0. So the answer is simply 2 pi, settled. Hence, we then have 2 pi integral from 0 to infinity of re minus r squared dr. So we then need to evaluate that other part now. So now evaluate integral from 0 to infinity of re minus r squared dr. Okay, so that means if you use substitution, if you say let u be r squared, then we say du is 2r dr. So an r dr now is simply 1 over 2 du. So we have r dr here. So r dr is 1 over 2 du. So, and if you put all of that together, integral from 0 to infinity of re of re minus r squared dr is now 1 over 2. So e minus u remains. Then r dr can simply go to du. So in this case, we can evaluate integral from 0 to infinity of e minus u du. So e minus u du is more like from 0 to infinity, right? E minus u du. So here, e minus u from integral from 0 to infinity of e minus u du. That's like if you integrate e minus u, you end up getting you get minus e raised to power minus u from 0 to infinity. Okay, so that's take out the minus, so you have e raised to power minus u from 0 to infinity. So this is minus e raised to power minus infinity minus e raised to power minus 0. Okay, if you put infinity first and then 0 later, that's minus e raised to power minus infinity. That's 1 over e raised to power infinity, if you don't mind. That minus 1 over e raised to power 0, if you like. Then this is minus 1 over e raised to power infinity is infinity minus 1 over e raised to power infinity is e raised to power 0 is 1. So this is minus 1 over infinity is 0 because x over 0 is infinity. So if you cross multiply, that means 0 times infinity is x. If you divide through by infinity, so this cancels out. So it means x over infinity is 0. So anything divided by infinity is 0. So that's why this is 0 and this is 1 here. So 0, so this is minus 1, minus into minus 1. And the answer is simply 1 there. So that's why e raised to minus u du is equal to 1 here. So it means this is half times 1, basically. So that means I squared now is 2 pi into half. So 2 cancels 2 here. So I squared is equal to pi. And because I squared is pi, then we can say, therefore, integral from minus infinity to infinity of e raised to minus x squared dx is simply square root of pi. That's how we come about the fact that gamma of half is equal to square root of pi over, yeah, like this. So since e raised to minus x squared is even, then we can say that integral from minus infinity to infinity of e raised to minus x squared dx is the same thing as 2 integral from 0 to infinity e raised to minus x squared dx. Now take note what's happening here. So minus infinity to infinity, what that means is minus infinity to infinity can be written like this. So integral from minus infinity to infinity can be the same as integral from minus infinity to 0 plus 0 to infinity. This is minus infinity to 0 and 0 to infinity. But since e raised to minus x squared is an even function, whatever x is, it's always the same. So we can say that's the same thing as integral from 0 to infinity for both. Okay. And that means you just then have 2 integral from 0 to infinity. That's exactly what's happening over there. So that you now have this whole thing as in 2 integral from 0 to infinity of e raised to minus x squared dx equals in square root of pi. And then integral from 0 to infinity e raised to minus x squared dx is square root of pi over 2. And that's how we have that. So that gamma of 1 over 2 now is equal to, if you remember, we stopped at where we have 2 times integral from 0 to pi, 0 to infinity e raised to minus x squared dx. So that means you have 2 times again, remember that integral from 0 to infinity of e raised to minus x squared dx is root pi over 2. Then we say gamma half is 2 times root pi over 2. That cancels out. So gamma half is simply root pi. Okay? Gamma half is simply root pi. So we have that right there. So it looks like a lengthy process, but we can see we have proven beyond all doubt that gamma half is square root of pi. And that's one of the most important relationships as far as gamma function is concerned. So we can also talk about half integer formulas now. So using the recurrence relation, gamma z plus 1 equals z gamma z. We already established that starting from the last video. We compute that gamma z over 2 now is simply, z plus 1. That means if you subtract 1, so you have half gamma half. And now we already know what gamma half is like. So it means that gamma 3 over 2 is the same thing as half times root pi over 2. This is 1 over 2, right? We know gamma half is root pi, so gamma 3 over 2 is root pi over 2 easily. Similarly, gamma 5 over 2 is 3 root 2. I mean 3 over 2, gamma 3 over 2. And we know gamma 3 over 2 from here is root pi over 2. So 3 over 2 times root pi over 2 is 3 root pi over 4. Like that. And then we have the reflection formula. So Euler discovered the reflection identity that gamma z is gamma 1 minus z. And that is equal to pi over sine pi z. Okay, so this formula analytically continues the gamma function into the complex plane. So this is what is called the reflection formula. So gamma z multiplied by gamma 1 minus z is the same thing as pi over sine pi z. So the formula analytically continues the gamma function into the complex plane. It also reveals the connection between gamma function, so we have gamma function there, trigonometric function, and complex analysis, in that z is a complex number here. then that's the reflection formula. For the example of reflection formula, now, if you set z to be half, in this case now, if z is half, so we have gamma half, then gamma half, gamma 1 minus half. So that will give you gamma half times gamma 1 minus half, and that is equal to pi over sine pi over 2. Since z is half now, so that's pi over 2, sine pi over 2. Thus, we can say that gamma 1 over 2 squared from what we have here is equal to, sine pi over 2, that's sine 90, which is 1. So that's pi over 1, which is simply pi. So you have gamma 1 over 2 all squared is pi. And that also establishes the fact that gamma 1 over 2 is root pi, just like what we derived the other time, using the reflection formula, which is gamma z into gamma 1 minus z equals pi over sine pi z. Then we have, so having talked about the reflection formula, we also have the duplication formula. So for the duplication formula now, Legend's duplication formula states that gamma z plus 1 over 2 is equal to 2 raised by 1 minus 2z square root of pi gamma 2z. So this formula connects gamma values as shifted arguments. So we then have the application of the example of the duplication formula. If z is half, so what happens? So you have gamma z into gamma half plus half, which is gamma 1. That is equal to, since z is half now, so 2 times half is 1, 1 minus 1 is 0. So you have 2 raised by 0, square root of pi, then 2 times half, that's 1 again, so gamma 1. And we know gamma 1 is 1 already. So here now, you have gamma half, gamma 1 is 1, gamma 1 is 1. So 2 raised by 0 is also 1. So we just have gamma half to be square root of pi. Another establishment of the reality that gamma half is square root of pi, which we proved lengthily. And of course, reflection and duplication formulas also establish those realities. Then for analytic continuation, now the integral definition only converges for the real part greater than 0, real part of z greater than 0. However, that's for positive real part. So however, the functional equation gamma z plus 1 equals z gamma z, extends gamma to almost all complex numbers. For example, if you have gamma of minus half, that can simply be, okay, what's basically happening here is this. If we have gamma z plus 1, that's z gamma z. Okay, I think I should write that out, right? So you have gamma z plus 1, which is z gamma z, right? Now, we say that, so if you need gamma z, it means that you can divide through by z. So you have gamma, okay, let me just do my normal thing. So gamma z plus 1 is divided by z will give you gamma z. Okay. So it looks like square, but don't it's not, because there's no, that extra tail isn't there. Okay. So means that we can have gamma z equals gamma. Okay, now the square root thing is trying to come. So gamma z plus 1 all over z itself. So in essence, we are saying that if we need gamma minus half, we can work it out. So that's gamma minus half plus 1 all over minus half. So that means we have gamma minus half plus 1 is gamma half all over minus half. And we already know gamma half is square root of pi, and now all over minus 1 over 2. So that means we can simply have this to be minus 2 roots pi like that, and we are good to go. So distinguish between gamma, very important. It's not the same thing as square root. Very important to note that. So that's minus 2 root pi right there. So that's what we have this. So it means this formula is so powerful that you can then apply, extend factorial to even fractions and non-integers generally. So poles of gamma functions. The gamma function has simple poles at z equals 0, minus 1, minus 2, minus 3, and so on and so forth. So this occurs because gamma z equals gamma z plus 1 over z. Division by 0 appears at negative integers. Now, see what that simply means. So let's try gamma 0, for instance, and see what happens. So imagine you want to do gamma 0. No, that should be gamma 0 plus 1 all over 0. That'll be gamma 1 all over 0. That's undefined. That's why it's a pole right there. What about gamma minus 1? That'll be minus 1 plus 1 all over minus 1. And that is gamma 0 over minus 1. So still undefined, and so on and so forth. So gamma of, yeah, that's gamma 0, right? So still undefined, like I said, that you have those poles going on like that. So this occurs because this division by zero appears at negative integers. So then we have residues of gamma functions. So we dealt with poles, talking about residues now. So at the poles, right, we know z is equal to minus n. So where n can be 0, 1, 2, and so on and so forth. So the residues are residues of gamma comma minus, and that's minus 1 raised power n over n factorial, And then the examples, imagine that at z equals minus 1, the residue is minus 1. At z equals minus 2, the residue will 1 over 2. Okay? So residue here is minus 1. The residue here is 1 over 2 as z equals minus 2. Then that takes us to the idea of Stirling approximation, and we get the full derivation of that. For large values of n, factorials grow extremely rapidly. So Stirling's approximation provides an asymptotic formula for estimating n factorial. So this result is n factorial is approximately square root of 2 pi n multiplied by n over e raised power n. So since n factorial is equal to gamma n plus 1, right? That's established because n gamma n is the same thing as n factorial. So the gamma function satisfies that gamma z is roughly square root of 2 pi, z raised to power 1. That's we are taking more like we're taking n to be 1 now. So square root of 2 pi z raised power z minus 1 over 2 raised power minus z. So for large z. So we now derive this formula carefully. So let's try to derive this formula we have here, this gamma z thing. So start from the gamma function as usual. So knowing that gamma n plus 1 is integral from 0 to infinity of t raised power n e raised power minus t dt. Then since gamma n plus 1 is n factorial, then we obtain that n factorial is integral from 0 to infinity t raised power n e raised power minus t. So n factorial is something as gamma n plus 1 established already. So we write the integrand, which is t raised power n e raised power minus t. And e raised power n uh, t raised power n raised power minus t can then be written as e raised power, if you carry this t on top of this t raised power minus t now, so you can have n ln t minus t here, all right, and then thus, we now have n factorial to be integral from 0 to infinity of e raised power n ln t minus t dt. Then we can scale the variable now. To scale the variable, we just introduce the fact that t is equal to nx. If t is nx, then dt dx is n. So that means dt is n dx. So anyway, you see dt, you put n dx. So we can then substitute. We know that n factorial now is equal to integral from 0 to infinity of e raised power n ln nx minus nx n dx. Because now t is nx. We just substitute that. So we expand the algorithm. So ln nx is simply ln n plus ln x. So hence we have n factorial, which is equal to n integral from 0 to infinity e raised power n ln n plus ln x minus nx dx. So if you distribute the n now, so your n factorial becomes n integral from 0 to infinity n ln n plus n ln x here minus nx, like that. So we can separate factors. So if you separate the factors, then you have that. So you bring out all the constants. So you have, because this one now, anything that doesn't involve x, you can move it out. So e raised power n ln n, you can bring that out. N is here already. You bring that out. But the parts containing x, that's e raised power n ln x minus nx. You keep that under here because the variable we are dealing with is x. So that and since we know that e raised power n ln n is n raised power n, so e raised power n ln n is as good as n raised power n. So we obtain that n factorial is n raised power n plus 1 because n times n raised power n is simply n raised power n plus 1. Integral from 0 to infinity e raised power n ln x minus x dx right here. And then we will write that n factorial is n raised power n plus 1. Integral from 0 to infinity e raised power n ln x minus x. So you are factorizing n here now, dx. Then we define the phase function. So we define that f of x is ln x minus x. So this ln x minus x right here. So then we have n factorial to be n raised power n plus 1 integral from 0 to infinity e raised power n f of x dx. So for large n now, so when the n is very big, the dominant contribution comes from the maximum of fx for large values of n. So we then find the maximum. So to find the maximum, we need to differentiate, right? F prime of x, f of x, we have f of x. So f prime of x will just be 1 over x minus 1. So if you differentiate, So, and then we can set f prime of x to 0. Let's say, how did f of x come in here? Okay, f of x originally was ln x minus x, right? So if we differentiate ln x minus x, we get 1 over x minus 1. That's what we have here. So to find the maximum, we set we equate this to 0. So we have 1 over x minus 1 equals 0. And that's, if you multiply through by x, that's like 1 minus x equals 0. That means x is equal to 1. So if you compute the second derivative, so that's 1 minus 1 over x squared. So if you evaluate that at x equals 1, we get f prime of 1 equals minus 1, and that is less than 0. That shows it's a maximum point. So if in case you're confused about this, you can check my calculus playlist to learn about maximum and minimum points like that. So you get a function, differentiate it, equate to 0, get the values. Those values are the critical values. Then now evaluate them in the second derivative. Negative ones are maximum points, positive ones are minimum points. The ones equal to 0 are inflection points. So therefore, we say x is equal to 1 is the point of maximum contribution here. So what do we then do? We now go for Taylor expansion around the maximum. So remember Taylor and Maclaurin series. I think we treated that under one of the previous playlists. Is it uh Okay, that must be, yeah. I mean, under different circumstances, especially under scientific computation with Python, I think. So Taylor expansion around the maximum now. So expand f of x near x equals 1. So using the Taylor expansion, you have f of x equals f of 1 plus f prime of 1 into x minus 1 plus 1 over 2 f prime of 1 into x minus 1 squared plus all that. So if you compute each term now, first, f of 1 is ln 1 minus 1, which is ln 1 is 0. So 0 minus 1 is minus 1. Next, f prime of 1. So substitute, uh, differentiate ln 1. That's 1 over x minus 1. F prime of 1 is 0. Next, f prime of 1 is minus 1. So if you just use the function the way it is, hence f prime of x is approximately minus 1 minus 1 over 2 x minus 1 squared. Therefore, you discover that the exponent of n f of x is approximately e raised by n into minus 1 minus half x minus 1 squared, and so on. If you separate the factors, then you have e raised by n f of x approximately e raised by minus n, right? E raised by minus n into x minus 1 squared all over 2. Then if you approximate the integral again, you substitute into the integral. N factorial is approximately n raised by n plus 1. E raised by minus n integral from 0 to infinity, e raised by minus n x minus 1 squared over 2 dx. Since the Gaussian is sharply picked near x equals 1, for large n, we extend the limits. So to 0, integral from 0 to infinity, e raised by minus n x minus 1 squared over 2 dx, which is approximately minus 8, minus infinity to infinity of e raised by minus n x minus 1 squared over 2 dx. Thus, n factorial is now approximately n raised by n plus 1 e raised by minus n integral minus infinity to infinity e raised by minus n uh, into x minus 1 squared over 2 dx. So if you evaluate the Gaussian, this is a lengthy thing, right? Evaluate the Gaussian integral now. So then we say let u be square roots of n into x minus 1, so that du is square root of n dx, and hence dx is du over square root of n. So if you substitute that, we have integral from minus infinity raised for minus n into x minus 1 squared over 2 dx equals 1 over square root of n, integral from minus infinity to infinity of e raised to minus 2 squared over 2 du. So using the standard Gaussian integral, this ends up being square root of 2 pi, just like very close to what we did with square root or gamma half, right? So therefore we have this whole expression now being equal to square root of 2 pi over n altogether. So the final simplification then comes that like this, n factorial is approximately n raised by n plus 1 e raised by minus n square root of 2 pi over n. Simplify powers of n now. So you have n raised by n plus 1 dot times, you have root n here, 1 over root n. And one of this whole thing is n raised by n plus 1 over 2. Hence, n factorial is approximately square root of 2 pi, the square root of 2 pi from here now, multiplied by n raised by n plus 1, n raised by n plus half, then e raised by minus n that you have here. Then if you factor that, n raised by n plus half is n raised by n raised by half. So if you put all of that together, then you have square root of n coming to this place, and then n over e raised by n. So, and that's where you get the Stirling formula from. So that n factorial for very large numbers is approximately square root of 2 pi n into n over e all raised to power n. So then, uh, talking about the gamma function form now, we say since n factorial is gamma n plus 1, we can replace n with z. So to obtain gamma z to be approximately square root of 2 pi z, because gamma functions here, we're talking about it about complex numbers in general. So you have gamma 2 pi z raised by z minus half e raised by minus z for large z. So example now, you want to approximate 8 factorial. So using Stirling for 8 factorial, right? We just say 8 factorial is already getting big, right? So you have 8 factorial equals is approximately square root of 16 pi, because now you have uh z is 8, so 2 times 8. So you have 16 pi, then okay, yeah, that's square root of 2 pi, then you have z raised power. Okay, I think we're using this general one now. N now is 8, right? Then 8 over e raised power 8. Yeah. So if you compute that, you have 16, square root of 16 pi is approximately 7.089. And then 8 over e raised power 8 is approximately 5765. So 8 factorial is then like 7.089 times 5765. And 8 factorial then gives you 40861. Now the actual value of 8 factorial is 4320. So the approximation is as close as possible here. But when the number gets bigger, it gets more accurate for sure. So don't forget the Stirling formula for approximating big factorials. So because if you have 100 factorial, for instance, imagine having to say 1 times 2 times 3 times 4 times 5 times 6 times 7 until you get to 100. That's a long distance. So instead of doing that, you can just fix up the formula here, just fix it up and do your thing. So you get the results before is multiplying all of that. So let's talk about the digamma function. The digamma function is a logarithmic derivative of gamma. So you have phi of z equals d dz of ln gamma z. So equivalently, phi of z is actually, when you differentiate this, and that's like when you differentiate a logarithmic function, you have phi gamma prime of z over gamma of z. So the digamma function appears in harmonic sum, statistical estimation, and quantum field theory. So then you have digamma identities. So for integers, phi of n is h sub n minus 1 minus gamma, where h of n is a harmonic number and gamma is the Euler's constant. So example, phi of 1 is minus gamma, for instance, because here that's n is 1. So h of 1 minus 1, that's h naught, which can be taken to be 0, and this is minus 1 right here. Then you have the polygamma functions. So higher derivatives are called polygamma functions. So phi power n of z is dn plus 1 over dzn plus 1 ln z. So the first polygamma function, of course, is phi 1 of z, which is called a trigamma function. So you have trigamma series given like this. The trigamma function has the series representation phi 1 of z, which is summation from k equals 0 to infinity of 1 over z plus k raised to power 2. And then you have example 1 here. Imagine you want to evaluate gamma 7 over 2. We know gamma 7 over 2 is the same thing as 5 over 2, gamma 5 over 2. And then gamma 5 over 2 here is, 5 over 2 is already here. So gamma 5 over 2 is now 3 over 2, gamma 3 over 2. So you keep breaking it down until you get something you can get a value for. And the value is gamma half is root pi. So gamma 3 over 2 now is half gamma half. So gamma half, you don't need to break it further because gamma half is already square root of pi. So you can then say 5 times 3 times 1, that's 15. 2 times 2 times 2, that's 8. Then gamma half is root pi. So gamma 7 over 2 is 15 root pi over 8. So example 2 now, you want to deal with gamma 1 over 4, gamma 3 over 4. So that may not, you probably don't know any expression where gamma 1 over 4 is, you don't know the value for gamma 1 over 4, but we have reflection formula, we have duplication formula, which you can revert to. So using the reflection formula, gamma 1 minus z is pi over sine pi over z. So since z is 1 over 4, so you have gamma z, gamma 3 over 4 right here. And that's simply equal to pi over sine pi over 4. Sine pi over 4 is sine 45, right? That's root 2 over, yeah, I think that's root 2 or so. So you have sine pi over 4 alone to be root 2 over 2. So that means you have pi over root 2 over 2, which is pi over uh that's 2 pi over root 2. If you evaluate that at the end of it, it's just pi root 2 for gamma 1 over 4, gamma 3 over 4. So don't forget in addition to the fact that gamma z plus 1 is z gamma z, don't also forget the reflection formula and the duplication formula. So we can do some Python codes to establish some facts. So if you want basic gamma computation and you want to calculate gamma 5, gamma 0.5, gamma 2.5, just import special swipe just from swipe out the special import gamma, then you just evaluate and print directly. So you have all these values. So gamma 5, of course, that's 4 factorial, which is 4 times 3 times 2, which is 24. Then you have gamma 0.5, which we found to be square root of pi, and gamma 5 over 2. I think gamma 5 over 2 is 3 root 2, 3 over 2 gamma 3 over 2, and then we just go on and we get 1.329493 and so on and so forth. Then for digamma, that's the integral of the log of gamma, right? I mean the derivative of the log of gamma. We have these values. So digamma 1 is this, digamma 5 is that. Then we have the polygamma also. You have polygamma 1 comma 1, you get that. Then you can also plot gamma function. So to plot gamma function, which we did under scientific computation with Python. So this is what that looks like. So when you plot gamma function, so see the process minus 4.925. So within a very short range because it can be quite wide. So you have this whole thing, this gamma function now. Then let's talk about some applications of gamma function. The gamma function appears in many areas, like in probability and statistics. You have gamma distribution, you have beta distribution. In the next video, we'll talk about beta distribution and you see how it's connected to gamma distribution. Then you have chi-square distribution, student distribution. Then you have complex analysis. You have it in areas like residue calculus, Mellin transforms, and zeta functions. In physics, you have quantum mechanics, statistical mechanics, and Feynman integrals. Then for geometry, you have the volume of an n-dimensional sphere, which is V sub n over r of r is pi n raised power 2, r raised power n, gamma n over 2 plus 1. Then in summary, we see that we have some important formulas. You have the Euler integral for gamma function, that's gamma of z equals integral from 0 to infinity of t raised by z minus 1 e raised to minus t dt. That's the fundamental thing from where we derive the fact that functional equation is the same thing as gamma z plus 1 equals z gamma z. And we have the reflection formula, which tells us that gamma z, gamma 1 minus z is the same thing as pi over sine pi z. Then we have the duplication formula that gamma z plus half is 2 raised per minus 2 raised by 1 minus 2z root pi gamma 2z. Then you have the residue formula, residue gamma comma minus n to be minus 1 raised by n over n factorial. And then you have the Stirling approximation. Gamma z is roughly square root of 2 pi z raised by z minus half raised by minus z. And you have the digamma function phi of z, which is gamma prime z over gamma z. So we have practice problems, and as usual, we're going to solve two of them. So we want to evaluate gamma 6. Of course, gamma 6, you know that to be 5 factorial, which is 120. You can compute gamma 9 over 2. So all you just do is you do 7 over 2 gamma 7 over 2. So you now have 7 over 2 times. So since you know gamma 7 over 2 is 5 over 2, gamma 7, 5 over 2, you keep going like that until you get to gamma half and you multiply out. Then show that gamma 2 is 1 using the Euler integral. So you just fix 2 for you just fix 2 into this expression. So Zena is just fix 2 here and ever and mod and do integration by parts or just integrate if possible directly and you get your values. So use the functional equation to compute gamma minus 3 over 2. Of course, we can use gamma z plus 1 equals z gamma z to establish this. Then you want to verify that gamma 3.5 is 2.5 gamma 2.5. Of course, that's correct because gamma 2.5 itself is actually gamma gamma 1.5, gamma 1.5, I think. Yeah. And then we continue until we get the 0.5 gamma 0.5, and we know gamma 0.5 to be square root of pi. Evaluate the improper integral. So this can easily be done because this is t raised per half e raised per minus t. Then evaluate this also. Prove that gamma z plus 2 is z plus 1 z gamma z. That's possible also. Then using the reflection formula, you can compute this. You can also evaluate this. Then use the duplication formula to simplify. You can do this. Just fix the values into the formula. Find all the poles of this, compute the residue of this, compute the residue of this, approximate 15 factorizing Stirling's approximation. Then you want to show that uh, limit as z approaches infinity for gamma z plus 1 over z gamma z is 1. Of course, that's possible to show. Of course, because we already know these two are basically the same technically. So evaluate phi of 2 given phi n is hn minus 1 minus gamma. That's like H2 minus, and that's H1 minus gamma. Then compute phi of 4. Then you want to show that the trigamma series, summation from k equals 0 to infinity of 1 over k plus k, 1 over 1 plus k all squared is pi squared over 6. Then using Vn over r equals this now. You want to compute the volume of the four-dimensional unit sphere. So let's go to solve two problems here. I'm taking care of problems 9 and 15. 9 is about using this reflection formula to compute gamma 1 over 3, gamma 2 over 3, and 15 is to approximate 15 factorial using Stirling's approximation. So let's go for those and bring this home. Okay, so I guess I need a change here. Let's go for something on the bright side. Let's go for this. Yeah, so problem 9 now, problem 9. So using the reflection formula, using the reflection formula, compute gamma 1 over 3, gamma 2 over 3. Okay, so solution, we have using Euler's reflection formula, right? We know that gamma 1, gamma z, gamma 1 minus z is the same thing as pi all over sine pi z already. So that means that, so now z is 1 over 3. Okay, so for z equals 1 over 3, we know that 1 minus z will be 1, 1 minus 1 over 3, which is 2 over 3. So it means that z is simply 1 over 3 in this case. So if we substitute now, we then have gamma 1 over 3, gamma 2 over 3 to be the same thing as pi over sine pi over z. That's pi z, right? Yeah, pi z. That's pi times 1 over 3. That's what will give us this, just like what we've seen here. So that means we have pi over sine pi over 3. Sine pi over 3 is sine 60 degrees. And sine 60 degrees is root 3 over 2. So that's pi uh, all over root 3 over 2. That's sine 60 root 3 over 2. So that means we have 2 pi all over root 3. So we can have this way, or we can rationalize. So that's 2 pi all over root 3 times root 3 all over root 3. So that means we have 2 root 3 pi, or to avoid confusion, 2 pi root 3 all over 3. Okay, root 3 times root 3 is 3. So we can have this way. Yeah, or better, we can leave it this way also. So that's uh problem 9 right there. So let's go for problem 15. That's the one with Stirling number. Problem 15. Problem 15 says to approximate 15 factorial using Stirling's approximation. Stirling's approximation. Okay. So here we have Stirling approximation is this: n factorial is approximately square root of 2 pi n, then n over e raised to power n. So that's what we need here. So generally here, we know that n is equal to 15. So since n is 15, we just substitute. So that means 15 factorial is approximately square root of 2 pi n, right? That's 2 pi times 15 into 15 all over e raised to power 15 right here. So that means that's approximately square root of 30 pi, square root of 30 pi, and then we have 15 over e, 15 over e raised to power 15, 15 over e raised to power 15. So yeah, I like to use, yeah, we can even use Google for this, right? Or let's use Desmos. Let's use Desmos and see what happens. Desmos. Yeah. So we go for the graphing stuff. So we need square roots we need square root of 30 times pi. So that's 9.708. 9.708. So this is 9.708 times 15 over E. Let's do 15 over E. 15 divided by E. That's 5.518. So 5.518 raised to power 15. So that's approximately 9.708 times 5.518 raised to power 15. So let's do that. So all this now raised to power 15. Okay, let me just go ahead. Raised to power 15. So that's 1.339 1.3395 times 10 raised to power 11. 1.3395 times 10 raised to power 11. Okay, that's what we have there. So at the end of the day, this one is approximately, we multiply everything out. We have 1.15 factorial, right? Is approximately 1.300 times 10 raised to power 12. So that's what that is. But what's the real thing? So we can just punch that straight and see 15 factorial. So that's 15 factorial. That's 1.307 blah 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 times 10 raised to power 12. So that's pretty close. Okay. So the real thing is the real 15 factorial. So to check if how close we are close enough, I believe. That's one 15 factorial is 1307 674 1307 6743 68000. That's 15 factorial. That's close enough because this is same thing as 1.3077 times 10 raised power 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So good enough. Yeah, so with that, we come to the end of solving the problems attached to this. So don't forget, check out the problems again and see how well you can handle them. So you have 1 to 4 here. In fact, 1 to 5, then 6 to 10, then 11 to 15, 11 to 16, in fact, and then the rest. So try your hands on them and let's see how helpful this is for you. Let me know how helpful this is. And if there's something else to let me try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you haven't subscribed, question is, what exactly are you waiting for? Why not go ahead and subscribe right now, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges you'll find out when you click. You know, ultimately, don't forget to comment, like, and share so that other people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Watch out for better function in the next video. Bye.